So when you invest some money in a savings account, you're probably going to invest it with what's called compound interest. And compound interest is really great because you don't just earn interest on the principal or the initial amount you invest. You actually get interest on the interest you earn every year, which lets the amount that you've saved grow exponentially. So here's an example. Let's say you invest $1,000 at 5% interest. So, and it's going to be an annual interest rate. So after 1 year, you will have gotten 5% of your $1,000. So 5% of $1,000 is $50. And you'll get to add that $50 to the 1,000 that you started with. So by the end of a year, you have $1,050. So if we think about what we did mathematically there really, is when we go from year 1 to year 2, you're multiplying by 1.05 or 105%, but as a decimal. Now this is, so you don't really notice compound interest yet, but in the next year is where we notice compound interest. So simple interest is where you would only get interest on the principal. You only get $50 a year, 5% of your $1,000. You just get that every year. But compound interest, you'll actually get interest not just on the $1,000 you initially put in, but on that $50 that you gained in interest in your first year. So instead of just getting another $50, I get just a little tiny bit more in that second year. It doesn't seem like much at first, but over time it really adds up. So in that second year, I'll multiply by 1.05 again. So you'll take the $1,050, multiply that by 1.05, and you get $1,102.50. So not much yet. In the next year, so from the third year to the fourth year, we multiply by 1.05 again. That gives us interest on not just the 1,000 that we initially invested, right, but also that extra $102 that we've already earned. So now we're up to $1,157.63, and it goes on like that. So if you think back to our discrete functions unit, what kind of a sequence is this? What kind of a sequence of numbers do you multiply by something every time? We're multiplying by a constant multiplier. Remember, that's actually a geometric sequence. I know this was a few months ago, so it might be rusty. So the formula for a geometric sequence is this. Tn, that's the nth term. So that would be, maybe if it was the fourth term, it would be the $1,157.63, is equal to T1, that's the first term, so that'd be like the $1,000, times R. R is the multiplier, that's the 1.05 that we're multiplying by every time, to the power of n minus 1, and n is the year number. So if I plugged in all the values that I have here, then Tn would be 1,000, right? $1,000 is what I start with, times the multiplier. Every year I'm multiplying by 105% as a decimal, that's 1.05, to the power of n minus 1. So that would be my formula for how much I have at this Tnth term. But in financial math, we actually count things a little bit differently. So instead of counting the first year when you put in that $1,000 as year 1, like in our discrete functions unit, we always make the first term T1. In financial math, we tend to call the first year 0, and then we count up from there. So that tweaks things a little bit. So instead of your formula being this, that T1 is 1,000 times 1.05 to the n minus 1, where n is your year number, or say Tn there. It just tweaks it a little tiny bit when we change the way we number our years. So instead of n minus 1 up here in your exponent, that'll simplify to just n. So this thing here will turn into this equation. Tn is 1,000, 1.05 to the power of n. If you think about that, right, if n equals 0, so the first year, the 0th year, then you'd have 1.05 to the 0, that's going to be 1, times 1,000 is 1,000. So that kind of fits with this way of numbering here. All right, that brings us to our equation for compound interest. So we don't use the symbols that are familiar to us in discrete functions. We don't use those in financial math, but the equations are based on the exact same math. So it just looks different, but it's the same underlying math going on. Notice that this thing out here is how much money you started with. That means it's the principal. So we call the principal the amount you initially invested, P. So we're going to start there. And then we have to multiply by, involves the interest rate, right? The 5 was the interest rate, but I have to make it a decimal. So instead of being 5%, I need to make it a decimal, 0.05. And I had to add 1 to it, right? Because I'm multiplying by 105%. So my multiplier is actually 1 plus R, where R is that annual interest rate converted to a decimal. So 5% becomes 0.05. This exponent up here was the year number, noting that we start the first year as being the 0th year. So when you first put the money in the bank, that's year 0, and then we sort of count up from there. And Tn, that's the amount that you have at the end. So we call that A for the amount you have at the end. So that right there is our equation for compound interest that we'll be using. Let's try an example with that. So I'll just write out our equation on the side here. So A is P is 1 plus R to the T. Now it's really important that we sort of figure out what everything is here. So let's say you hope to have $20,000 in 10 years. You invest at a 3.7% annual interest rate. We want to know how much do you need to deposit today. So first, the $20,000, that's not what you're depositing now, right? That's not what you have in the bank right now. That's what you hope to have in the future at the end. So that means that is A. So P is how much you invest right now. A is how much you hope to have at the end. So A is equal to that $20,000. 10 years, well, that's the time that's gone by. So put T is 10. The 3.7% annual interest rate, that's R, but we need to convert it to a decimal. So instead of 3.7%, it's going to be 0.037. So to convert a percentage to a decimal, just divide by 100%. The thing I'm trying to find is how much I need to deposit today. That's P. So that's your principal. Your principal is what you need to put in the bank today. All right, so here's our equation. Let's plug everything in. So A is 20,000. P we don't know. R is at 0.037. And T is 10. We can clean this up a little bit. So do your brackets first. So 1 plus 1.037 will be 1.037. That's to the power of 10. Do your exponents next. So do the 1.037 to the power of 10. That gives me this here, 1.438. And I actually just keep that whole number in my calculator so I don't clear that off, so that I don't make a rounding error. Then you want to divide both sides by the 1.438, so that'll cancel out there. So 20,000 divided by the 1.438 gives me P. So right now I would need to invest $13,907.29 in order to have $20,000 in 10 years if it's growing at a 3.7% annual interest rate. Let's try one where we're trying to find the interest rate itself. So let's say we deposit $5,000 today. So how much you deposit today at the beginning, that's P. So P is equal to 5,000. And you'd like it to grow to 10,000. So that's your goal. You want it to double. So we want that to grow to 10,000. And you'd like that to happen over a time frame of 8 years. And we want to know what R is. What is your annual interest rate here? So let's set up our equation again. So A, the amount you have in the future, is your principal that you're investing right now, times 1 plus R to the T. We're trying to solve for R here. So let's plug everything else in. The amount you want is 10,000. The amount you have right now is 5,000. And you're hoping this happens over 8 years. We're trying to isolate for R. So you want to get everything away from the R. The first thing you want to move is the 5,000. So divide both sides by that. That cancels out the 5,000 here. 10,000 over 5,000 is 2. Now I need to get rid of this 8. If you remember from our exponents unit, how do we get rid of an exponent? Well, you can put both sides to the power of 1 over 8, right? And that is going to 8 times 1 over 8, right? That would cancel and make just 1 here. Then you'll just be left with 1 plus r on that side. This is also another way of saying it is you're taking the 8th root of both sides. So I'm left with 2 to the power of 1 over 8 is equal to just 1 plus r. So you want to actually do 2 to the power of 1 divided by 8. Just a pro tip, when you're putting this into your calculator, make sure you put the 1 divided by 8 in brackets. Otherwise, your calculator will do 2 to the power of 1, which is just 2, and then it'll divide that by 8. So you'll get totally the wrong answer. So make sure you do 2 to the power of, in brackets, 1 over 8. And that gives me 1.0905. That equals 1 plus r. My last move is just minus 1 from both sides. Right, to get the r on its own. And we get r is equal to 0.0905. Now that's the interest rate as a decimal. To make it a percentage, all you have to do is multiply by 100. So that's going to be 9.05% as the annual interest rate there. Let's look at this graphically. So let's say Ashley invests $100 and she invests it for 4 years at 8% compound interest. If we were graphing how much she has over time, the graph will kind of look like this. So after 1 year, she'll have $8 more. After 2 years, she'll have not just another $8, so she won't be just like up 16 because she'll get interest on the initial 8 as well, and so on, and it keeps growing from there. So if I wrote an equation for how much she has over time, I'd say the amount that she has is equal to her principal. Her principal was $100 times 1 plus the interest rate, which is 0.08, to the power of time, however much time has gone by. And in this case, it's 4 years. But I'm going to keep it as a variable so that I notice something. That time variable, which is what's on my x-axis, is in the exponent. This is an exponential function. And so compound interest is exponential growth, and that's how your savings are able to grow to so much over time. Exponential growth gets faster and faster and faster over time. So in the first few years, you might not notice it that much. Your savings don't seem to be growing that much. But 40 years down the road, the exponential curve means that your compound interest has really paid off. All right, now it gets a little bit more messy than that in real life. So it turns out that not all savings accounts are compounded annually, and that's actually a good thing. The more compounding periods that happen per year, the more chances you get to have interest on interest. But it makes our math a little bit messier. So we said that T is just the number of years. That's not quite true. So if something is compounded more or even less than once per year, so let's say something is compounded monthly, then T is not going to be the number of years that go by. It's actually going to be the number of compounding periods. And I'll show you an example soon of what that looks like. But as soon as you change T, that actually also has to change the definition of R too. So R is going to become the interest rate for one compounding period, or per compounding period, instead of per year. So I'll just show you what that looks like. Let's say you have, so let's say you have a 5% interest rate, or annual interest rate, but it's compounded monthly. Maybe for, let's say, 4 years. Right, so then T in that case is not going to be 4 years. It's how many compounding periods there are. And this is compounded monthly, so that's 12 times per year for 4 years. So t is actually going to be 4 times 12. So the total number of compounding periods here is actually 48. And r is no longer going to be 5% or 0.05. It has to be that interest rate split up over 12 compounding periods in a year. So it has to be 0.05 divided by 12, which is 0.004167. So my R value that I'm going to plug into this formula is the interest rate for a single compounding period, not for the whole year anymore. All right, let's try a whole problem with that. So let's say Michael invests $1,200 at 5.5% interest. It's compounded quarterly, so that means it's compounded 4 times per year. First, what is P? So P is the principal. This part doesn't change. Michael invested $1,200, so that is the principal there. T is the number of compounding periods. So he invests this for, it's coming up, 6 years. And there's 4 compounding periods per year. So we have to do 6 times 4 to get the t value. So it's the number of compounding periods per year times the number of years gives you t. So that'll be 24. R is the interest rate, but not just the 5.5%. So it's not just 0.055. We have to split that interest rate up over all the compounding periods in a year. We have to see what is the interest rate per compounding period. So I have to divide that by 4 to get R. So I take the 0.055, divide by 4. That gives me 0.01375. All right, we want to know how much does Michael have in 6 years. So that's an A value. I'm looking for the amount in 6 years. And I know my formula is this, P times 1 plus R to the T. So you can actually just plug everything in now. So P is 1,200. R is the 0.01375. And T is 24. So you want to do your brackets first. So add the 1 to this first. Then do the exponent, put it to the power of 24. And then multiply all that by 1,200, the principal. And after 6 years, Michael's investment has grown to $1,665.41. There we go. So how much interest did Michael earn over that time? To find out the amount of interest, all you have to do is take the amount that you have at the end and subtract off how much Michael initially put in. So Michael initially put in $1,200. He ended up with $1,665. So how much interest did he earn? Well, it was actually just the difference between those two values. So you're just going to take the 1,665.41 minus 1,200, how much Michael initially put in, and that gives you $465.41 that Michael earned in interest through this.